Hi, welcome to the course. In this course, there are two main subjects that we will study. One is probability, and the other is statistics. These are very related subjects, but they are still different. So let's start by thinking about what is probability. Okay, so probability is the mathematical framework for computing probabilities of complex events. That's a mouthful. And we make an assumption that we know the probability of the basic events. What precisely do we mean by probability and by event? Those will be defined later in the class. For now, let's just think in terms of common sense. Okay, so let's think about a simple question. We flip a coin, and we get tails. We flip it again, we get heads. Okay. What we believe somehow is that the probabilities are equal. But what do we really mean by that? What does that mean? Does it mean that we'll exactly get the same number of heads and tails? No. It just means that if we flip the coin many times, then for some very large number of coins that we flip, let's say 10,000, we'll get the number of head is approximately or about 5,000. Okay, that's what we expect. But what do we mean by about? Okay, how can we express this notion of about in a better way? Because we might be actually interested in knowing how far from that we are. Okay, so we're going to simulate coin flips. We'll use a pseudo-random number generator to simulate coin flips. And instead of heads and tails, it'll be more convenient to use 1 and -1. And then the number of heads relates to summing all of these +1 and -1. And what we expect is that the sum will be 0 or close to 0. So we will vary the number of coin flips, which we denote by k. And here is a little bit of code for generating such random coin flips. Here we're generating the coin flips themselves, and here we're summing the coin flips along a particular sequence. We're generating many sequences at once, and this is the number n that we say here is by default 100. So this is a central part of the code, but I'm not going to show you all of the code. To see that, you have to download the notebook yourself and play with it to see the details. So here is a histogram that shows for flipping a coin 1,000 times, what is the distribution of this sum that we said. The sum is about 0, but as you see, it's not exactly 0. And every time that I rerun this experiment, what you see is that the histogram that you get is slightly different. However, even though it is each time slightly different, there is something very much in common for all of these coin flips. They're all concentrated around 0, but they're not exactly 0. And for this number of coin flip, 1,000, it is extremely unlikely that there are below 250 or above minus 250 and above 250. Okay, so with probability theory, we can calculate how small we expect Sk, the sum, to be, the absolute value of the sum, because it can be either negative or positive. And what we will show, is that the probability that this Sk is larger than 4 times square root of k is extremely small. It is 2 times 10 to the minus 8, or 0.000002%. So we'll have to flip the sequence of 1,000 coins many times before we can see that it will be bigger than 4 square root of k. So let's actually do the simulation and see if that is the case. Okay, so here is our simulation. What we see is here we have 100 coin flips, here 1,000 coin flips, and here 10,000 coin flips. And the red line mark what probability theory says is the boundary in which it is very, very likely that the total number of coin flips resides. Okay, so I can rerun this experiment too. And you see that, again, each time the distribution is somewhat different, but it never goes outside of the red bars. Okay? So that's consistent with what we said. Now, here it seems that all of them are very similar, right? It doesn't really matter if you do 100, 1,000, or 10,000 coin flips, but that's really because I'm scaling it according to this boundary. So the boundary here is minus 40 to 40. Here it's minus 100 and something to 100 and something, and here it's minus 400 to 400. If we scale, if we plot the full scale of these coin flips, what we see is the following. We see something like this. So when we plot the whole scale from minus 100 to 100 for 100 coins, and from minus 10,000 to 10,000 for 10,000 coins, then we see that the distribution becomes more and more concentrated around 0 relative to this scale. Okay? So if I run it again, you get each time a different distribution, but you get that the distribution is more and more concentrated if you flip the coin more and more times. And the width of this is square root of k, or 4 times 2 times square root of k. So you see that the more coin flips more times you flip the coin, the closer it is relatively to the range to 0. Okay, so let's summarize. We did some experiments where we summed k random numbers that correspond to coin flips with probability xi. So we had xi minus 1 or plus 1 with probabilities half and half. And our experiments show that the sum is almost always in the range minus 4 square root of k to plus 4 square root of k. Okay, so we can write it this way. If k goes to infinity, we have 4 square root of k as the range divided by k. So that is 4 divided by square root of k, which is equal to 0, which goes to 0 as k increases. And so what we can say is that sk relative to k, so the ratio of the number of the difference between heads and tails divided by k, that goes to 0. And that's basically what we mean by the probabilities being half and half. Okay, so again, what is probability theory? It's the math involving proving in a precise way the statements that we made above. Okay, so before we just kind of did simulations and alluded to something that we'll prove in the future, but that's really what probability theory is proving these in a precise way. In most cases, we can approximate the outputs, these probabilities, using simulations. These are called Monte Carlo simulations, and that's essentially what we did in these little experiments that we did. So why isn't that enough? Because, first of all, calculating the probability gives you a precise answer. And doing Monte Carlo simulation just gives you an approximation, and you need to run the experiment longer and longer to get more and more accurate answers. And the second is that it is much faster than Monte Carlo simulations, essentially for the same reason. Okay, so that is a quick description of what is probability. And next time, we're going to talk about what is statistics. See you then.